Hello, welcome to Chemistry Chapter 13, the final exam review. You will need the final exam review worksheet and your Chapter 13 tables handy and a calculator. So let's go through these. Number one says, what's the delta H for the following reaction? And we want to use the bond energy method. All right, so let's write down the reaction. We have CH4 plus 2O2 yields CO2 plus 2H2O. Now we need, with the bond energy method, to have the Lewis structure. So for CH4, you'd have a carbon in the center and then 4 single hydrogen bonds. And then for oxygen, O2, that's a double bond. And then with CO2, carbon would be in the center, and you would have a double bond of oxygen on each end. And we don't need the electrons. I'm just doing that because it feels like it's the right thing to do. And then with H2O, oxygen would be in the center, and we would have a single hydrogen bond on each side of the oxygen. So the delta H using the bond energy method is just the energy of the reactants minus the energy of the products. So all the other formulas in Chapter 13 is products minus reactants. But with the bond energy method, it is reactants minus products. Okay, so let's go through this. So delta H is equal to, so we have, if you'll get your sheet, we have a 4 C-H bonds at 411 kilojoules per mole. So the coefficient is 1, so we have 1 mole times 411 kilojoules per mole, and then there's 4 of those bonds in that molecule. We want to add to that 2 moles, and in this case we have 1 double bond with oxygen. So if you look at your table and you want to find that O double bond O, it's 494 kilojoules per mole, and their 2 is because of the coefficient, so 494. Now we're going to subtract out the 2 products. So minus 1 mole for CO2, and there's 2 O double bond C's. Okay, so that's going to be right here, 799. And then, of course, there's 2 of those bonds, so 799 times 2. And then, finally, we're going to subtract out 2 moles. So we're on the water now. And we have each H-O bond is 459. And then there's 2 of those. Okay, so delta H is going to be 1 times 411 times 4, so 4, that'd be 1644, plus 2 times 494, that'd be 1,000 minus 12, so 988. And then 1 times 790, that would be 1,600, so 1,598, so minus 1,598. And then 459 times 2, that's going to be 918, times another 2 would be 1836. All right, so let's go ahead and put that in the old calculator. So 1644 plus 988 minus 1598 minus 1836 is negative 802. And then the unit would be kilojoules, because your moles would cancel, your moles cancel, and what's left is kilojoules. So it's negative, that's exothermic. The problem didn't ask that, but indeed it would be exothermic. That makes sense because this is a combustion reaction, so it makes sense that it would release heat and be exothermic. All right, let's see if we can fit number 2 on the board here. So number 2 says, what's the delta H for the following reaction? We're going to use Hess's law this time. So we have C2H6O in liquid form plus 3O2 gas. That yields 2CO2 gas plus 3H2O gas. And we do need the phases because the table has those phases in it. Now delta H, standard conditions, is equal to the sum of the enthalpy of formation at standard conditions of the products minus the sum of the change in enthalpy of formation standard conditions of the reactants. So we're going to start on the product side. So we have, for CO2 gas, we have 2 moles. And then we're going to look it up in the table. So in the table, find table 2, enthalpies of formation. CO2 is right here. It's negative 394 kilojoules per mole. We're going to add to that 3 moles. We're at water gas. So if we find water gas, it's the very first one, negative 242. And now we're going to subtract out the 2 reactants. So 1 mole for C2H6O liquid. Just make sure you're on the right table. Table 2, negative 278. And then for oxygen, O2, any element in its natural elemental form, oxygen appears in nature as O2, has an enthalpy of formation of 0. So that would be minus 0. All right, so we have 2 times negative 394 plus 3 times negative 242. And then 2 negatives that make a positive, so it'd be plus 278. That's negative 1236. Kilojoules. All right, just make sure you use the right table. Be careful with your calculator, but not really all that hard. You're on using Hess's law, you don't have to draw the Lewis structures, so it's really a simpler process. You do have to remember, though, that it's products minus reactants. All right, excellent. All right, so in fact, I think maybe on that one that oh, never mind. Okay, number 3 says identify the reactions drawn on the board as endothermic or exothermic and determine the activation energy. So when I was the classroom teacher, I would just make up a couple of graphs on the board. So we'll just make that up here. It may be different than what your teacher does, but let's draw an energy diagram. So on the y-axis, we would have energy in kilojoules, and the x-axis reaction coordinate, that's really just time. So let's say we have a graph that looks like this. And let's say up at the top, that's 100. And right here, let's say that's 50. And then down here at the bottom, let's say that's 20 kilojoules. So the question says, is it endothermic or exothermic? So we need to get delta H. And you want to take the right side of the graph minus the left side of the graph. So that's going to be 20, right? It's a 20 here, minus 50, which would be negative 30 kilojoules. So that is negative. It releases heat, so it's exothermic. Now the activation energy it's the top of the hill, which is 100, minus the left side, which is 50. So to get this reaction going, we have to add 50 kilojoules of energy. So that'd be the activation energy. All right, let's do one more. This time, let's do one that looks like that. So we have kilojoules on the y-axis, time on the x-axis. So let's say this is 50 this time, and up here this is 100, and this would be 80. So delta H is the right side, which is 80, minus the left side, 50. So that's 30 kilojoules. It's positive, so it's endothermic. So it gets, after this reaction, things get colder. It doesn't release heat, it absorbs heat from the atmosphere. All right, and then your activation energy, it's going to be the top of the hill, 100, minus the left side. So I probably should have put some different numbers there just to shake it up. But 100 minus 50, also 50, just like the one before. All right, but that's an endothermic reaction versus an exothermic reaction. All right, that does it for number 3. You'll probably have to draw or at least interpret on the final exam some energy diagrams. So number 4 says determine the sign of the entropy in each of the following reactions. So just to remind you, we're going to do the right side minus the left side on the reaction. Gases have the most entropy. Solids have the least entropy. So we have solid zinc plus HCl. So that's aqueous. That yields zinc chloride. And then that liberates hydrogen gas. So pretty famous reaction that's often a demonstration. Pretty cool demonstration in class. Okay, so the sign of the entropy. We're going to do the right side minus the left side. Okay, the right side has a gas and an aqueous substance. The left side has a solid and an aqueous substance. So the right side has more entropy than the left side. So we would have more minus less. Anytime you have that, you have a positive situation. All right, a positive number, so it's positive. And the reason would be gas on right, or product side. Okay, B is nitrogen gas plus 3H2 gas, and that yields 2NH3 gas. So they're all gases this time, so we can't look at the phase. We have to look at the number of moles. So on the left we have 1 plus 3, we have 4 moles. So just adding up the coefficients. On the right we have 2 moles. So again, the sign of the entropy is the right minus the left. And in this case, 2 minus 4, or less minus more. Anytime you have less minus more, you're going to get a negative. And the reason is more moles on the left side, or the reactant side. All right, and then C, we have 2 silver nitrate. All right, that's aqueous, plus magnesium hydroxide, also aqueous. That yields silver hydroxide, which is a solid, plus magnesium nitrate, and that is aqueous. Okay, so we're going to be using the phases since we have different phases. Going to do right minus left. Okay, the right has a solid and an aqueous, and the left has 2 aqueous. Think of aqueous as think of it like a liquid. So what we have on the right, again, is products minus reactants. We have less entropy on the right, so it's less minus more. That's going to be negative. And if you had to give a reason, you could say it's because there are solid on the right. Okay, so that's how you do it. Let's go ahead and do a mathematical problem about entropy. We know that entropy is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. Okay, so we have been given this equation, 4NH3, so that's ammonia gas, plus 5O2 gas. That yields 4NO gas plus 6H2O gas. Okay, so we're going to be using, and then we are given in the problem that the delta S for O2 is 205. Okay. So the change in entropy, so we need to put that delta there, is going to be the right side, so 4 moles. And for NO gas, we're going to consult table 3. That's the entropy table. NO gas is 211 joules per mole K. Going to add to that 6 moles H2O gas. First one, 189. Then we're going going to subtract out 4 moles. We're on the reactant side now. So NH3 gas, 193. And then subtract out 5 moles. And that was, according to our problem, 205. It's not in the table, but everything has an entropy. So, all right, let's try this out in the calculator. So we've got 4 times 211 plus 6 times 189 minus 4 times 193 minus 5 times 205. So that is negative 180. Is it negative? No, I'm sorry, it's positive. So that's positive 181. And then the moles cancel, so moles, moles. So the unit is joules per Kelvin. You don't want to miss the unit and get a bunch of minus ones on the test. Or even more if you're in chapter 14 or 15 than minus 1. So be careful about the unit. Okay, so I'll clear the board here. And we've just got a couple left to go involving Gibbs free energy. All right, number 6 says if a reaction has a delta H of 150 kilojoules per mole, and the delta S is 300 joules per mole K, at what range of temperatures is the reaction spontaneous? Well, if you see range of temperatures, you're not going to be using table 4. You're going to be using this equation. All right, the delta G is equal to delta H minus T delta S. So that's an equation you'll need to memorize, where temperature is in Kelvin. Okay, so our answer will be in Kelvin, a temperature range. So we need delta G to be negative. So I'm going to change this to an inequality. To be negative, 0 is greater than delta H minus T delta S. So 0 is greater than. Now in the problem it says that delta H is 150. Now I'm not going to write down the units because it gets a little messy here. And that delta S is 300. All right. Delta H is kilojoules. Delta S is joules. So 300 joules is equal to 0.3 kilojoules. You divide by 1,000. So it'd be 150 minus T times 0.3. Okay, so 0, let's make this a little nicer, is equal to 150 minus 0.3 T. Now I'm going to add 0.3 T to both sides. Okay, so plus 0.3 T plus 0.3 T. So you would get 0.3 T, and because you're not dividing or multiplying by a negative, you don't have to flip the sign, is greater than 150. So T is greater than 150 over 0.3. So 150 divided by 0.3 is 500. So our answer is T has to be greater than 500 Kelvin. So you have to has to be pretty hot in order for this reaction to be spontaneous and to occur. Otherwise, it will violate the second rule of thermodynamics. Okay. All right, number 7, we'll finish this up. So number 7 says, is the following reaction spontaneous at 298 K? So anytime you see 298 K and spontaneous, those two words, you know we're asking for Gibbs free energy at room temperature. And in that case, we use table 4. So we have CaO solid plus CO2 gas, that yields calcium carbonate, CaCO3, which is a solid. So we know that our change in Gibbs free energy it's similar to Hess's law in terms of what it looks like. It's the sum of the Gibbs free energy of formation of the products minus the sum of the change in Gibbs free energy of formation of the reactants. Okay, so we're going to start with the products. We have 1 mole, and we're going to look in table 4 for calcium carbonate, CaCO3. It's right there, so it's negative 1129. And that's kilojoules per mole. Going to subtract out 1 mole, and then CaO solid, if you look in your table, is at 38.2. And CO2 gas, so that's also 1 mole. So everything's got a number on this one. Now, if there were O2, H2, anything like that, it would be 0 because it follows the same rule as the enthalpy of formation. So we have CO2 gas, finding that, it's right here, negative 394. Okay, so that's going to be negative 1129 minus 38.2, and then 2 negatives make a positive, so plus 394. So that gives me a Gibbs free energy of negative 773.2 kilojoules. So is that spontaneous? Yes, it is spontaneous since delta G is negative. So this reaction can occur at room temperature. And that is all I have for, that's a good review. If you can do these problems, then you are in good shape for the final exam for Chapter 13. All right, I'll talk to you on the next one. We'll do Chapter 14, 15, and 16, a video for each one. And hope you have a great day.